let's talk about torque. Torque is something that produces rotation. So it does have to do with force, because force makes things accelerate. And as we know, we can have angular acceleration or rotational acceleration. So we know that force will help things accelerate. So force does have something to do with torque. However, again, torque produces rotation. So it's not just the force that provides rotation, but it's also where that force is provided. Because, so for example, look at this door with this hinge on it. If I exert a force right at the hinge, is the door going to rotate? Absolutely not. Handles on doors are here at the other edge for a reason. Because if I exert a force right at the other end, like the very other end in the hinge, then we're going to have lots of torque because it's going to rotate. So I apply that force there, there's lots of torque. So again, it's not just force, but it also depends on where you apply that force. What I'd also like you to go do right now, go to a door right now. Obviously, we'll wait till I'm done explaining this, and then go to a door and try this. But try pushing a door from its middle instead of its very edge where the doorknob is. Okay, and tell me if it's easier or harder. Okay, so you did it. I'm assuming everybody paused the video, did it. So it's harder to push it from the middle than it is from the edge. And when it's even more difficult is if you push it like right there. So go try that. Y'all paused it, yeah? And you tried that. So if you try to push a door from like right beside the hinge, oh my goodness, there's barely any torque happening. It's really, really difficult. You need more force in order to move it at that point, right? To produce that same amount of torque. So how far away it is from the hinge and how far away the force is from the hinge really matters. But also, of course, direction matters, because if I then all of a sudden push it in that direction that's like parallel to the door, and you're basically pushing it into the hinge, well, is there any rotation there? Absolutely not. So of course, it also depends on what direction I'm applying the force. So again, torque is something that produces rotation, a force that produces rotation. But of course, like we have already figured out, where we apply the force and in what direction we apply the force definitely makes a difference as to whether something is going to rotate or not. Okay? So that distance from the turning axis to wherever you're pushing it, that's called the lever arm. So that's really, really important. Okay, so that lever arm really does help us figure out how much torque is happening. So right now our lever arm R is that long, but in this case it was half as long, right? So that is definitely going to inform torque for us. And also then, of course, the direction in which we apply the force really does matter. So we only care about really forces that are perpendicular to the door, to whatever the thing that's turning. Okay, so if the force is not at a right angle to that lever arm, then we only care about the perpendicular component, because that's the only thing that's contributing to torque. Okay, so in this thing below where we have our force going that direction, well, since it's at an angle, there's a component that's of course parallel and there's a component that's perpendicular, and we only care about this force that's perpendicular. That's the only one that's really contributing to torque. Okay, that's what we care about when we're talking about torque. We care about how long the lever arm is. We care about the force in the perpendicular direction. And so that's going to bring us to our equation for torque here, which is R. R is the lever or moment arm, times F, and then we got a little perpendicular sign there, and that is, of course, force. And torque is, we use this Greek letter tau for torque. Okay, T-A-O, yeah, there we go, tau. And that is the letter that we use to represent torque, okay? So there we go. We have torque is equal to R times F perpendicular, and of course, if we do want to get our perpendicular force, if it's not apply directly perpendicular, then you're going to need to multiply by sine or cos theta. So in this one with the sine theta, that theta will have to be the angle made with the lever arm. So you could see a situation in which you need to multiply by cosine theta. It really just depends on the angle that you're given. Okay, so just keep that in mind. Always draw a diagram and go from there, because you guys, as long as you draw that triangle, you know the difference between when you need to use sine and cosine, okay? But again, where you pull on something really does make a difference. So for example, with this wrench here, if you only pull at that point, you're not going to get as much rotation as when you pull at that point. Or you'll have to get the same amount of rotation, you're actually going to have to apply more force. Okay, so if we want the same rotation, we're going to have to apply more force in that first situation than we would in the second situation. So if you're ever trying to rotate something and it's really sticky, then what do you need? You need a longer lever arm in order to apply less force. So that's why a lot of the time with wrenches, they do come with extenders. And of course, as long as like it attaches nicely, and that can, where it attaches can withhold the force, then if you then apply that, extension arm to it and apply the same force, it's more likely to turn than if you were to be, I don't know, pulling this at an angle or pulling it straight up at its regular end. So just something to try next time you're trying to loosen a really, really tough bolt. Just make your lever arm longer and you should be able to put in the same amount of force, but then actually possibly move it and see it rotate. Okay, so let's do an example with torque and how we can use torque to calculate different things, calculate forces and things like that. So a bolt on a car engine needs to be tightened with a torque of 35 newtons times meters. Oh, by the way, let's talk about the units for torque really quickly. It's meters times newtons. It can be also newtons times meters. Just a really quick thing. It's not the same as joules, except for it is, except for it isn't, except for it is, except for it isn't. So it's technically the same makeup, except for when you see newtons times meters or meters times newtons, you know we're talking about torque. If you see joules, you know we're talking about energy or work. Okay, so just a really annoying thing there, but so technically they have the same units, but for torque, we just leave it as meters times newtons or newtons times meters. For energy and work, we actually put it as joules, okay? So we got 35 newtons times meters, which of course is our torque. We use a 25 centimeter long wrench and pull at the end of the wrench, okay, so that's good. But at an angle of 60 degrees from the perpendicular. Well, that sounds kind of stupid, I'm not gonna lie. Why would you pull it at such a weird angle? But I don't know, sometimes, you know, you need to get into tight spots and maybe that's the only angle you could. Okay, I'm gonna draw a, you know, what are these things called? It's called a diagram. That's a really normal word and a weird one to forget, but that's what I'm gonna do right now. Okay, here's your wrench. Okay, of course we know this guy is 25 centimeters right there. And you are pulling with a force of 60 degrees from the perpendicular. So maybe something kind of like this. And remember it says from the perpendicular, so there's the perpendicular, so that's going to be your 60-degree angle right there. So like I said, always just draw the diagram to help you figure out if you need to use sine or cosine. Because that's the force, and then this is, of course, the perpendicular force, which is what we care about. So if I really do want to get my perpendicular force, that is on the adjacent side here. So that is going to be force times cosine of that 60-degree angle, because of course in this case we have our perpendicular force is on the adjacent side, not on the opposite side. Okay, so we know that torque is equal to R times the perpendicular force, which we found was F times cosine theta. Okay, and there we go. There's our equation. And we have everything except for force. So let's rearrange to find force. Don't forget to convert that centimeters to meters. We always still want meters at this point. And then if we do that, we get 280 newtons. In this case, we want two significant digits. So that's going to be 2.8 times 10 to the 2 newtons. And there we go. That is our answer. That's the force that needs to be applied. But of course, if you could just apply perpendicular force, you need to apply much less force than 280 newtons. So just let that be a lesson to you. Try to pull on things perpendicularly when you're trying to produce a rotation. Okay, so let's talk a little bit about balancing things, because balancing things is kind of an interesting thing, because what's happening when you balance something, right? And in this situation, it's not always holding it right at the middle. Basically, you just need the weight to be the same on both sides, so the force of gravity to be equal on both sides. But of course, weight alone doesn't produce a rotation. Here, torque does, right? It really is a balancing of torques that needs to happen. How do we know that? Because we have a force and we have a pivot point that produces, look at that lever arm. So this is what we call the fulcrum right here. That is the turning axis. So that's the point at which it would rotate perfectly in, I guess kind of a circle or an oval in this case. So again, balance is achieved if that torque that produces clockwise motion is the same as the torque that produces counterclockwise motion. So again, it's not just balance of weight, but it's a balance of torques as well. And that's how we can then use something like this to see where this fulcrum, that pivot point, needs to be on something. So let's do an example like that. So say we have two students, they're 56 kilograms and 43 kilograms. I'm going to call this guy student number 1. And I'm going to call this guy student 2. And they want to balance on a 1.75 meter long seesaw. So we want to know where they should place the pivot point. So again, diagrams. Diagrams are always great. So we have student 1 over here. He's heavier, so it's probably going to need to be near to student 1. If you've ever tried to balance anything, usually if one end is heavier than the other, your fulcrum needs to be closer to that heavier point, right? So for example, I don't know, say you have a pen with a lid on it. The end with the lid on it is a little bit heavier, so usually you need to, in order to balance that pen on your finger, which obviously you can hear I'm trying to do right now, you need to hold it a bit closer to the end with the cap on it, okay, in order to balance their weight. All right, so again, we got student number 1 over here, student number 2 over there, and then we have the distance, the lever arm for student 1, we'll call that R1, and the distance for the second student from the fulcrum, that's going to be R2, okay? And those two together should give you the total length, which was 1.75. Okay, so there we go. So there's some setting for what's going to happen here. Now I want to know where they need to place the pivot point. So I need to find R1 or R2. Doesn't really matter, right? It's just, you'd say, okay, you place it this far away from student 1 or this far away from student 2. But that's what you're basically having to do. So again, not only do I know that their weight needs to be balanced with the seesaw, but it's easier to think of the fact that their torques need to be equal and opposite. So the torque for student 1 needs to equal to the torque for student 2. I don't know why I'm writing it all the way over there. Let's do this. Okay. So what does that mean? Well, torque again is R times the force perpendicular. Okay, oh, I should call that R1, R2, force perpendicular. How are we going to get that perpendicular force? Oh, well, the force that's really being applied here is what? They're force due to gravity. That's the perpendicular force here. So, instead of doing this, I'm going to do R1 times M1G equals R2 times M2 times G. 1 and 2 just being student 1, student 2, so we can keep that a little bit straight here. The G's actually cancel out. So we're making progress, but we still aren't there because we still have two unknowns. We don't know R1 or R2. So what we really need to do is get one of those in terms of what we know. Looks like I've already sort of started that up here. If you look at this R1 plus R2 is equal to L, oh, well, we can rearrange to solve for R1 or R2. It doesn't really matter, right? But since I can do that, actually, sorry, I'm just looking that in my notes I solved for R2, so I'm just going to keep that consistent. So let's solve for R2. That's L minus R1. All right, so if we've done that, then we can substitute that in for R2 over here. Oh, and then we'll have everything in terms of R1, and then we can solve for that, okay? But again, it doesn't really matter if you solve for R2 or R1. Okay, so that'd be L minus R1. Okay, this is a pretty fun one to rearrange, and by fun I mean, you know, there's a few steps. So here, just follow along with my steps as I go along here. So first I'm going to distribute the M2 through there. And then in these situations where we have the thing that we want in two places, we have to get all those onto one side of the equal sign. So I'm going to add the R1 M2 to both sides. And then I'm going to factor an R out and get R1 times M1 plus M2 equal to L times M2. And then I'm going to divide both sides by that. So I should get R1 is equal to L times M2 divided by M1 plus M2. Isn't that a fun equation? All right, so let's plug all our numbers in. And what do we get? We get 0.76 meters to two significant digits. And then if you solved for R2, you would have gotten 0.99 meters. And either one is fine, as long as to kind of answer the question, you signify the fact that the fulcrum needs to be, or the pivot point should be 0.76 meters away from student 1. So there we go. That's how we balance people on a teeter-totter if they really want to be balanced. But of course, that's why teeter-totters do just have it always in the middle, because the most fun part about the teeter-totter is not balancing, but going up and down and up and down. So there you go. So it would only need to be in the middle if you had the exact same weight, right? If both people did. And then even if they do, then you still make it go up and down by applying extra forces that mess with our net force, of course. So that still can happen, where you can still balance on a regular teeter-totter. You just have to be with somebody who is exactly the same weight. So of course, and then if you have the same weight, then how do you still get it to rotate? Well, you need to have a net force that isn't zero, basically, or a net torque that isn't zero. So of course, when more than one torque that acts on a body, that's when you're going to have angular acceleration. Okay, and that is proportional to net torque, just like force is proportional to acceleration. Of course, torque has to do with force. Now we know it doesn't only have to do with force, but it does have to do with force. So that net torque is proportional to acceleration. Of course, net torque is just like we've always done net anything, right? It's the sum of all the different torques, where if they're in the same direction, directions here being clockwise and counterclockwise, then you're adding them. And if they are in opposite directions, then you are subtracting them. You're finding the difference. Okay, but remember that is proportional to angular acceleration, which is weird because our symbol for proportional to and angular acceleration is the same. So I'm just drawing one that's skinnier, I guess. I don't know. But still, that's all you got to know for now, though, is that they are proportional. Let's talk a little bit more about center of gravity. And we're going to go over this even more in the next lesson, but I'm going to start talking about it now, because that's what we were basically just doing with this teeter-totter thing. We were trying to find the center of gravity for this seesaw if these two students are on it, right? We're trying to find that center of gravity. So what is the center of gravity? Well, that's the center of the object's weight distribution, where the force of gravity is acting the same in every single position around that point. Okay? So it's the point in which any object is in a perfect balance, no matter how it's turned or rotated around that point, the center of gravity is the same. So that's basically right when you're trying to balance the pen or the pencil on your finger, that is its center of gravity. Although technically its center of gravity would be then inside the pen or pencil. So when you get into three-dimensional objects, it's actually really difficult to find the true center of gravity to something, which is why it's still pretty easy to topple that pen or pencil over your finger, because you're actually not at the true center of gravity, but you're just really close to it. Okay, and so for nice, easy shapes like a rectangle, center of gravity is really easy to find because it's just the center of all its sides. But then when you get into weird looking triangles or semicircles or things like that, the center of gravity can be a lot more difficult to find. But again, it's the place at which then, if you look at every single point, its force due to gravity is the same at every single point that's equidistant, right, from that point. So, there we go. So if we want to talk about torque in your center of gravity, well, if you don't have a base support beneath your center of gravity, an object is going to topple. Okay, so what does that mean? Well, if you try and touch your toes just normally, what happens? Your center of gravity, by the way, is your belly button. Well, yeah, typically it's your belly button. So that's your center of gravity. So we need some base support beneath that belly button if we want to touch our toes. So what happens when you touch your toes? Well, your butt juts out just a little bit, right? And then you can go and touch your toes. So basically, you still have that base support beneath your center of gravity, which is at your belly button, except for like actually in the middle of you. So like inside your stomach, but it's neither here nor there. But if you stand up against the wall and then you try and touch your toes, well, guess what? Your butt can't poke out a little bit. And I know you're all going to want to go try it right now. So pause the video. Go try it. Did you try it? Did you topple over? If you didn't, you need to comment below. And also, I just don't believe you. I think you cheated. Like, you need to stay flat up against the wall the whole time that you try to touch your toes. And if you don't topple over, then you have a weird body whose center of gravity is not in their belly button. And I don't understand you. So that's what it means, where we need base support beneath the center of gravity. And if you don't have that base support, the object is going to topple. Okay? If the direction of force is through the center of gravity, the force can do is move the object as a whole. So for example, again, go back to the pen and find its center of gravity, right? So here's my pen, right? With a little tip on the end. And then its center of gravity will be pretty close to the center, right? So if that's the center of gravity, so if you are holding that pen at its center of gravity and then you move your finger around, it's just going to move the whole pen. It's going to move the entire object. It's not going to topple. Okay, but then if I apply a force that's off center, say I like apply a big force right there, and then I move my finger away really quickly, what's going to happen? It's going to spin around this center of gravity, this axis, right? And it's going to spin and then fall all the way down to the ground. Now this point, the center of gravity, is just going to have like a nice linear, like its position to the ground is just going to be straight down, right? But like here, either end, its position with respect to the ground is not going to look like that at all. It's going to be like this, right? Because it's going to be going up and down as it goes down. So just something to think about, a few cool things about center of gravity. And then we're going to talk a little bit more about center of gravity and the way that mass is distributed around the center of gravity and how that affects something, torque and rotation. And we're going to talk about that more in the next lesson. But for now, that's all I'm going to tell you about torque. So good luck with doing some examples on torque.